Guys, this will be a short video to help you to why you should look at the 4-hour video. Looking at this image presented by OSHA, and we've seen this before, but now I have the symmetry I've been looking for forever. Now I can give you all my conclusive files on this. If you take note of this tape, this ruler shows approximately 3.5 inches at this face here of the concrete. If we look at the face of the concrete here, we see around 4 3/8 inches right here. So we've got about an inch, a 7/8 inch elevation here. This appears to be even greater elevation if we slide it down. If we can, for clarity, if we look over here, you see that this is higher than this one. If this was shear pushing off 12, it would be off not an upward motion as we see here, but it would be down, DOWN, down towards the pier in this case. Why do we have upward force? This is on 3/14/2018. There is no post-tensioning inside the structure on this date. Not until tomorrow, 3/15, does this happen. Post-tensioning. So we're without post-tensioning in the deck. Again, this is why you should watch my longer video. They moved it down. He moved it down here, and we see the elevation difference is 1/4 inch. This gap, I'll explain all of this in that 4-hour video, or perhaps I'll just do a bunch of short videos. I'll explain every single gap, why this gap is actually, because he can put tooling in it, is a tension break, meaning it's not compression going on here, but he's showing he can put apparently a wedged pair of scissors into the bottom of number 11 on 313. If this was in compression pushing off the number 12, how is it that he's able to put his calibration tool in there, if you will? Calibration tool being it's a pair of scissors at this point. I'll explain all these cracks in that 4-hour video, or perhaps I'll just do a little short excerpt every other night. And this one will be trying to explain to you that how number 12 is not being sheared off, but how 12 is being pushed back towards number 1. Imagine if you could put your hand at the top of 12 and push it over. These are over the joints, across the top of the joints there. Yes, I do know about clamping force and the friction that you're going to have to overcome. But that would explain why, if you were pushing it back, it would explain why the cracks on the deck are higher and not lower. It would explain why this has tension cracks and not compressive cracks. It would explain every single crack if you could create the one action that I just spoke of. And in the 4-hour video, I can get you that action. And the gist of it basically is you go to the top of here, you push over 11, the top of 12 rather, and you start getting a hinge point inside the diaphragm area. The hinge point, and this would show you all of this, including it cracked like hell when the detensioning took place. That after detensioning, that allowed the canopy to readjust towards number 1. And when I say the canopy specifically, I mean number 12. The top of number 12 was able to take an action towards number 1, the top of 12. This created everything you see here, including the symmetry of the bottom of the diaphragm. Let me explain that simply again. When you crank that, this would now give that the hinge action dropping down and hinging, dropping down and hinging. You got to watch the longer video. Dropping down and hinging back would give you this uplift of the outside of the number 12. Let's take a peek at that again from the top view. There's the crack, the drop down. That gives you a separation, and the drop down is clearly identified with the tape measure. The tape measure here is showing approximately 4 to 5 inches on the left, which we know is to be the northwest now, with a symmetrical break, meaning 1, 2, 3 in this pattern, same as the other opposite side of the deck. This is the northeast. This is the symmetrical break on this side, 1, 2, 3. And also the tape measure here showing approximately 3 to 3.5 inches. showing that it dropped down and more so to the right, identified further by the failing further down the bottom here. This is what happened is number 12 dropped down. And it dropped down because I'm going to show you quickly something quickly. Let me go to the back, the last image is down here. Bear with me. And so this is what the symmetry looks like at that failure as it's dropping down, creating all this symmetrical load here. This could be considered some type of box shear because the load's transferring of number 12 though, not 11. Not 11 pushing off 12. I'll give you little tips like this is the bottom of 11. The rest of 11's here. You can do the math at that point. Let me pause the video. As the OSHA report shows, as it states, the diaphragm was poured along with the deck. The diagonal 12 and 1, I'm sorry, the diagonals 2 through 11 plus 1 and 2, the uprights, were poured at another pour along, and the third pour was the canopy. The last pour was the blister bars. These are the joints that would be allowed for movement at the deck, at the underside of the canopy, of course, at the blister bars. We don't have so once you have 11 post tensioned, this 12. I'm going to show you this in a better image. So let me do this. Bear with me. If you watch the longer video, you won't get any problems. So as you look at number 11, 12 interaction, 11 and 12. Number 12 is stops at the diaphragm. If we follow the deck rather, follow it over to this point and come up. This is number 12. Therefore, this is also the joint of number 11. This was poured in one pour, as it's stated in the OSHA report. But what I want you to take note is the bottom of 11 and the top of 11. This is what I think they referred to as number A in the post-tensioning bar schedule, and this would be B. You can get that reversed. I believe B is the longer one by just a touch. A is only inside the decking. Number B, letter B, post-tension bar B is in the goes through the diaphragm slightly and inside number 12. Number 12 is what it's holding. So imagine now that they're post-tensioning. I'm trying to zoom in for you guys. Apologize for this. So imagine when they're post-tensioning number 12. I'm sorry, number B, number 11 and 12 are together. When they're post-tensioning, the anchor point for A at post-tensioning is in the decking. The anchor point for B is literally inside number 12. Here's 12 coming all the way down. Remember, 12 also has that bump out. The back of 12 has a bump out, making it wider, 3 foot, 3/4 inch, I believe. But again, and that is in that bump out, we have B. So I want you to look at the clamp. Think about this as clamp force. Let me get you the other diagram of the diaphragm. Hold on. So this is the diaphragm. This is 12. This is alignment of 12, along with the pipe going through it. This is the tie down for the diaphragm. That was not done as far as we know. All right. So let's go on. I want to get you that's the back span. I need to get you the span here. So this is very important to look at. So this is A. As you're post-tensioning these two guys together, as we were instructed, they did it at 50 kips per revolution, evolution. So we could go to the crane operator company now and say, hey, did you move that crane? How many times did you move the post-tensioning equipment back and forth? Did you move it equivalent of, say, 300 kips? Did you move it 6 times per lift back and forth? Total of, would that be 11 or would that be 12? You start off at 1 and back and forth. Is that a total revolutions of 12? the crane operator says, no, I just moved it twice, we know now that they just loaded this 100% at the kips twice, once 1 and 2, and just moved on. We could look at the timeline possibly and try to guess that too, but I could not get that data anywhere else. You guys are awesome. You might be able to find it. But now imagine the kips. Let's use 300 kips, okay, just to keep it round, so we know back and forth. The kips in the lower part, post-tension bar, which we know now to be in the deck, and it does that loop like this. OSHA shows it. NTSB shows it. That anchor point is inside the deck. The other anchor point is inside the number 12. Think of this as a clamping force. A clamping force, not just a post-tensioning bar for overhang. It's a clamping force now. Now let's go ahead and release this clamping force. What happens when we release the clamping force and the deck? That would be A. Well, the forces are released in this transverse longitudinal post-tension canopy stresses are lightened up at this interaction. And the same with B, but more so, once you release B, you no longer have the clamping force to hold number 12 onto the diaphragm. At that point, the dead load of this can just drop down. Now, the dead load of it can drop down. And would that dead load not look like something like this as it dropped down? And as it dropped down, it would create another moment of wanting, and that moment would, I believe, cause the top to rack towards number 2. Possibly post-tensioning in number 2 was already applied, as they stated. I don't know. That one I don't know. We don't really know this back and forth. This would explain all these cracks, though. There's a forensic hinge back here. Remember, that's the guy that invented it, Denny Pate's partner. Linda Figg's father's partner. So this is what we're looking at. This is a clamping force inside here, anchored inside 12. This is B. The other one is anchored in the deck, as I just showed you. You release the clamping force. The deck is still okay, but the clamping force is no longer holding 12 against the decking. Remember, when they put this together, this clamping force, if you will, it had already in place temporary shoring and all. So they never took the shoring down and removed tension off number 2 and 11 and to see how this would react. So yes, it was over there in the staging area, and they had it temporarily dead load checked. But they did not have a dead load checked with the post-tensioning removed off of 2 and 11. Had they done that, this should have exhibited itself in the same capacity over there. So there is the problem, that they dead load checked it, but only with the post-tensioning installed in 2 and 11. As the words say, it cracked like hell right here. This was after removing the tensioning. The crack like hell happened after they removed the clamping force in number B, I believe. That released the clamping force of 12 to lower itself, and also take a moment towards number 2. Yes, there's clamping force down the deck, but obviously the clamping force was not great enough to stop this from doing a lean towards number 2. This is what we're looking at here, not a shear. When they released the post-tensioning, so they had hundreds of thousands of pounds of clamping force on 11. If anything, we would have seen the shearing happen at that point, because there's an extra 100, maybe 600 to 1 million pounds extra on number 11. It would have cracked at that point. That's your shearing action. You have an extra 1 million pounds of force going down 11. But you're releasing that 1 million pounds of force, if you will. What you did was you actually released the clamping force of 12 to stay against the diaphragm. And that explains why you're seeing opening cracks here. This is tension. These are tension cracks with the hinge action happening at the deck. And this is just, you're looking at it peeling away, hinging forward. This is why these cracks, the bottom of this is facing closer to us, and this is further away, because it's taking a moment towards number 2. That's why this depth, again, explains the depth. And while also it's higher up there. why it's higher here. Because it dropped down, slid down a little bit in that compartment inside. I'm calling the compartment inside here in this diaphragm area. And then it rocked forward. Back to number 2. And this is why you can see 4 inches here, or almost 5 here. Because this lowered down. This explains the Daddy Pate's intention now, why he wanted grout underneath of here. This would have stopped once you remove that clamping force. 12 is somewhere in here, right? Somewhere about here somewhere. 12 was holding, B. The post-tension bar B was somehow holding 12 into the diaphragm. When he did that, it released it, allowed the dead loads of 12 to drop down. The dead loads, it could not hold itself on the deck. There wasn't enough development or interaction with the deck to hold it. So it did that cam action, along with whatever forces made it go towards number 2, perhaps the post-tensioning, and number 2 across the top of the canopy was able to pull it. But I just see we're looking at a hinge action and not shear going through. That's why we have it higher here. This is why if you lean it forward, back ass end would come higher up. You would drop down and then lean forward. So that would be the 2 charges that took place. 2 charges, 2 moments that took place. That also would explain all of this, why these, I keep screaming, are tensile cracks and not compressive. It has to be compressive if you're getting shear. This would also explain why we see, if you're looking close, looks like a brown fresh concrete. That the 4 inch we see on one side and 3 inch on the other shows the moment that took place, a slight twist, torquing action in the canopy at number 12. A slight rotation down by 1 3/4 inch in difference based on that tape measure at the pier and underside of the number 12 diaphragm area. It explains why this is gapped away also. That slight torque, that drop down, that 2 inches on one side, or almost 2 inches on one side greater than the other side, explains this. Remember that I just showed you that number A is down at the bottom here. A is here, 12 is up here going into, B is going into 12. And A is on the lower part. That's how I can explain all of this action, all of these tension movements. The slight drop down and rocking away. That's how you get the opening. That's how we get this, and you guys can extrapolate. If you watch my 4-hour videos, it shows more of the path. But number 1, this would explain it here too. This is the pipe, the drop down, the hinge action, and the rebar cover. That's a tension. That's an opening, not a compressive failure. It explains all of this opening. And let's do one more thing. And I'm going to terminate this video. I guess I might be around 20 minutes or so now. I don't know. It explains it all. The dropping away. Why, if it's shear, why didn't the concrete break these pipes all? Because it was not shear. It was a drop down first. You could call it a punching shear of number 12, pulling down. Now, when it did that, dropping down to that degree, and that bar was connected, it would have then loaded the canopy with whatever forces at the top of number 12, 12 and 11, 11 and 10. That bar would have still had the nut on top of it, would have gone back into play, and that's probably what's stopping this from falling all the way down to the pier at this point. That means the loads are now at the canopy pulling down on 10, which is also pulling down on 11. And it's restraining number 12 from falling all the way to the pier. Please, guys, I hope you're willing to share this and don't take it personally over the other forums, and see it for what it is. Let me get to the bottom of the page here, and this will explain. If you look at my 4-hour video, 2 of them. I'm sorry for the drama on that. It will explain all of this, and that's your bump down. It stayed in path of there. I'm sure some of you already watched it. Hundreds of people watched already. So here is the bottom of 11. See how 11? That's in the diaphragm. Correction. It's in the decking. Number 12's in the number B is in number 12. And again, when it dropped down, it pulled into canopy. This one did not. If you had a shearing effect, of number 11 pushing out. Well, this doesn't show that because here is the bottom of 11. Part of bottom of 11 is A, and there it is right here. Barely can see it right here. The bottom of, there it is. It's intact. You don't see it blowing out even the mortar here, and the face, and it's tight to the face behind there as it appears. So if anything was going to create that shear, it would only be the top of 11, and we're only talking about 9 inches. If you look at my video and you extrapolate from here, you see that, well, that's the bottom. This is also in line with 12. Everything beyond that, when I just showed you, beyond here, everything beyond this point is 12. And when you detension this, you lost the clamping force of holding 12 against the diaphragm. It dropped down. It then created this nut probably then is now stopping it from dropping down all the way. It's now jacked right there, and that created a new shock load or force that might have had an effect of whatever it's doing. So what's holding up the entire load of 12 now is going down 10. And so the intent was to put back this the way it was, would it be the clamping force, put it back to it was, which would pull number 11, pull number 12 back into the diaphragm action. But the cat was already out the bag at that point. I'm going to stop the video, but I want to show you, is that GG? GG would be, or is it BB? That A and B of the, there we go. So here's A and B, GG. So here's GG, this is 11, this is A and B, and this is what I'm calling A and B. So this, believe this is A and it's B. If you look at the post-tensioning bar schedules, it's like 1 or 2 inches long or something menial, but it matters for what you're looking at, A and B. For what I'm referencing, I'm calling this A and this B. And now you see what happens when you detensioned. They lost the clamp force. These being hinges, it allowed, once you lost that clamp force, obviously that amount of clamp force can now allow a action. I think number 12 did a lean towards this way. Yes, we have clamp forces in here, but I think it racked that way. This is at a plumb also by 2 1/4 inch or something. If you can find it on the other part of the drawings here, you'll see that they designed this at a plumb. It'd have been nice if they'd have measured that. I'm going to terminate the video because I'm enticing you guys to look at my longer video, but I'm also now giving the other forum energy to see something differently. Thanks for watching, guys. Love you all. Love you all.